A satisfactory photographic print is obtained when exposure time is 10 seconds at a distance of 2 meters from 60 candela lamp. The time of exposure required for the same quality print at a distance of 4 meters from a 120 candela lamp will be how much that we are supposed to find out. And here there are two cases. In first case, the lamp is 60 candela. In second case, the lamp is 120 candela. And what we need equal in both the cases? The answer is the quantity of light, the quantity of flux required for photography should be same. If the quantity of light or the total flux should be same, then how do we calculate quantity? The quantity is proportionate to time, intensity, and it is inversely proportionate to square of the distance. And this square of the distance you should be very firm of. That means that you should know that whether it is power 1, power 2, power 3 or what. So in the case of light, just as Coulomb's law, gravitation law, we have square of the distance. Okay, if this is quantity of the light and this should be same in both the cases, then we have an equation in case 1 and in case 2. In first case, intensity is 60. First case, the time is 10, and the distance is 2 meter, 2 square. That is equal to, in the second case, the intensity of light is 120 candela. The time we will give, we have to find out. So time is t. And the distance is 4 meter. So we write it 4 square. And now we get an equation. Okay, so this is physics. The quantity of light should be same in both the cases, and the quantity depends upon proportionate to intensity, time, and inversely proportionate to square of the distance. And now we can find out time. Time is equal to, here it goes, 60 into 10 into 16 divided by 120 multiplied by 4. So here it goes 20. So the time is 20 seconds, and let's check it. Here it is at the option D, 20 seconds. Thank you, and let's go to the next question. This relates to optics. In a vessel of depth 15 centimeter, liquid is poured till the liquid level appears to be at the half of the depth. Okay. A vessel of depth 15 centimeter, liquid is poured till the liquid level appear to be. This is the important word. At half of the depth. That means if the total level is 15, till the liquid appears to be at half of the depth. 7.5 appear. The liquid level is 5 centimeter. Now we have to convert these words of the text into the optical words what we use. What do we use? This appears, so we can call it, this is apparent depth. This one. Apparent depth, then what is this? It is given. The liquid level is 5 centimeter. That means this is the real depth. Oh, 5 centimeter from the top. So, not this 5 centimeter, we have to take this 5 centimeter from the top. So, where is the liquid? Here is the liquid. So this we will call as real depth. Real. Okay, and how much is this real depth? 5 from the top, so this is 10 centimeter. This is real depth. This is apparent depth. And now it's very clear. We have understood it, and we know the refractive index of a liquid. In such cases, so our answer is 4.3, and if we convert it into decimal, it is 1.33. Let's check the solutions, and here we have 5 solutions, and the right answer is here 1.33. That is what we have got here. Thank you. Let's go to the next question. Here is similar type of question. A camera objective has an aperture diameter D. The aperture is reduced to diameter D by 2. Okay. So there is a lot of decrease here. Now this is the new aperture. The exposure time under identical conditions of light. Identical conditions of light should be made. What does that mean? Same thing. The quantity of light on the photographic plate should be same. Energy required is same. Then only we get a correct picture. And for that, what is our formula for quantity of light? That is intensity multiplied by time divided by square of the distance. And this should be same in both the cases. But here the distance is same. A camera objective has an aperture diameter D. The aperture is reduced. This. Here is the area involved. Area. And we find there is no area here. So let us search for another relation. And that relation gives the intensity of light, intensity multiplied by area multiplied by time divided by distance. But in both the cases distance is same. So let us avoid the distance from the very beginning. We need not write it. So intensity into area into time in the case 1 is equal to in the case 2, or you can write it square of the distance, and this gives the quantity. Intensity of light, area, time. These are proportionate things which give us more quantity of light, and square of the distance which decreases the quantity of light. Okay, so in case 1, intensity is same, distance is same. Area into time in case 1 should be equal to area into time in case 2. Why we are not writing these two? Because these are same in both the cases. So just to make the thing simple, area into time case 1 is equal to area into time case 2. In first case, area is pi r square. So we will call it pi d by 2 square. When the diameter is d, the radius is d by 2. So this is area pi r square into time 1. Time 1, is it given? No, that is time t, 1. is equal to area 2. Now this has become for this internal circuit, yes, here, reduced to diameter d by 2. So this has become pi d by 4 square. This is new area multiplied by time t2. So what we are supposed to find out? We are supposed to find out the new time should be how many folds. So the new time t2 is equal to, we bring it on this side, pi is cancelled, and what we get here is d square upon 4 divided by d square upon 16 and t1. So this is equal to, d square is cancelled, this gets inverted, and this is 4t1. So the time must be increased 4 folds, 4 times than the t1, and here is our answer, D. The time should increase 4 times. So this is again related to exposure. And now we go to the next question. The frequency of a light wave in a material is 2 into 10 to the power 14 Hertz and wavelength is 5000 angstrom. The refractive index of material will be, there are 4 options. We have to find out what? Refractive index. And what is given to us? Frequency and wavelength. We know that frequency and wavelength together, they form velocity. Velocity is equal to frequency into wavelength. So velocity is given to us and we have to find out refractive index. So we remember the formula of refractive index with reference to velocity, and that is refractive index in a medium, that is equal to velocity of light in vacuum and velocity of light in the medium. This we must remember, and we should not invert it. So velocity of light in vacuum is known to us, that is 3 into 10 to the power 8, because this is a constant. We can use this value, but velocity in the medium is not given to us. But we know that frequency multiplied by wavelength is equal to velocity. So here we write frequency multiplied by wavelength, nu into lambda, and then we can put the values of nu and lambda. So this will become equal to 3 into 10 to the power 8. This is to be divided by frequency, that is 2 into 10 to the power 14 Hertz. 2 into 10 to the power 14 Hertz. Frequency do not change whether it is vacuum or material. So it is given in material, that doesn't matter, and then this is to be multiplied with lambda, and the value of lambda is given 5000 angstrom. So we write here 5000, but this is in meter per second, this is per second, so this also has to be converted to SI system, and 5000 angstrom is equal to 5000 into 10 to the power minus 10, and now it has become meter. So this is meter per second, this is per second, and this is meter. So you see meter per second is cancelled. So unit wise we have made it correct. Now this is equal to, here it remains same, 3 into 10 to the power 8, and this is to be divided by, here you see 5 into 2, that is 10, multiplied by 10 to the power, here it is 14 and here it is minus 10. 14 minus 10 is equal to 4. So that we write here as, 14 into minus 14 and minus 10 is 4, 5, 6, 7. So that is 10 to the power 7. See it once again. This is 10 to the power 3. This is 14. 14 and 3, 17 minus 10. That is 7. So we have written here 7. Now this 10 to the power 1 and 10 to the power 7 makes it 10 to the power 8. and that 10 to the power 8 is cancelled with this, and what we get here is 3. So refractive index of the medium is equal to 3, and we have an answer here. Here it is 3.00. So this is answer B is the correct option of this. And now we go to the second question. The next question is, a small coin is resting on the bottom of a beaker filled with a liquid. You see a beaker here, it is given, okay. A ray of light from coin travels up the surface of the liquid and moves along the surface like this. It goes along the surface here. Now this is a case of critical angle. We have studied, and where is the critical angle? Critical angle is made here. If we put a normal here, this is the normal. So C is the critical angle. Okay, but what we are supposed to find out? Here we have to find out moves along its surface. This is meter per second. So this is velocity, or question is bit incomplete. I should write here velocity of light in medium. And we are to find out velocity of light in the medium, that is this way. Okay, now again here velocity of light is there, and we know velocity of light is connected to the refractive index, and we also know that critical angle is related to refractive index. So refractive index, we have two relations. Refractive index is 1 upon sine C. This is what we remember from the topic of total internal reflection. Okay, so this is critical angle C, which is here. Now we know mu of a medium is equal to velocity of light in vacuum and velocity of light in medium. Okay, now here 1 upon sine C. C is here. We must know the value of sine C. Now if geometrically we see, if this is angle C, then these two are parallel lines, and this is also angle C, alternate angles. So this angle is equal to this angle. Why? Because this is inside the triangle. In this triangle, if this is the angle, then we can always find out its sine. Sine is this upon this. And how much is this hypotenuse in this right angle triangle? This is 3, this is 4, so this has to be 5. Pythagoras triplet. Okay. So now again, what is sine? Perpendicular upon hypotenuse, 3 upon 5. So I write it here, 1 upon 3 upon 5. This is equal to, I don't have to write it, mu is equal to velocity in vacuum 3 into 10 to the power 8. This is a constant, meter per second. Velocity in medium, this we are supposed to find out. So we write it V. And now in this equation, we can very well find the value of V. Let us correct it. This 5 will go here, 5 upon 3. So this is 5 upon, this V we transfer here. So this is V is equal to 3 into 10 to the power 8, and this 3 upon 5 we can transfer here. This will be multiplied by 3 upon 5, and this is 9 upon 5 into 10 to the power 8, and this is equal to 9 upon 5 is 1.8 into 10 to the power 8 meter per second. So this should be the speed in medium, and this we are supposed to find out 1.8 into 10 to the power 8 meter per second. So option D is the correct option in this question. And now we go to the next question. Two thin lenses of focal length f1 and f2 are in contact and coaxial. the power of the combination. Okay, it's a very simple question. Combination of two lenses. In the combination of two lenses, it is a test whether we remember the formula correctly. What do you know? There are two formulas in this. The same formula written two times, that is power of a combination is equal to power of lens number 1 plus power of lens number 2. But if we write it in the terms of focal length, then this is focal length of the combination f is equal to inverse of this. Power is 1 upon focal length. This is equal to 1 upon f1 plus 1 upon f2. Now what they are asking, power of the combination. This we are supposed to find out, power and not f. So we write it simply like this, that power is equal to, but this is given in the terms of focal length. So we convert them into focal length. So 1 upon f1 plus 1 upon f2. Get the LCM f1, f2. f1 plus f2, and this is power, this is our answer. So remember, in the hurry you should not invert it, because if they are asking what is focal length of the combination f, the focal length of combination is invert of this, because if you write this 1 upon f, then for finding f you will have to invert it, and that is equal to f1 f2 upon f1 plus f2. Okay, so this is not asked. What is asked? Power. So this is our formula for the power, very simple one. So we find it here, C. So right option is C. So this is only to test whether we know the difference between power, focal length and relation between the two. And now we go to the next question. Two periodic waves of intensity I1 and I2 pass through a region at the same time in the same direction. Two periodic waves are passing through a region. There is a region here, one wave is passing in this direction and other wave is passing in this direction. And they interact with each other, and we know that with interaction there will be superposition. Okay, the sum of the maximum and minimum intensity. The maximum intensity is there when there is a constructive superposition, and the amplitude will be, if the one wave has got amplitude A1, other has amplitude A2, then the resultant amplitude for superposition will be A1 plus A2. Okay, and the minimum will be A1 minus A2. So A maximum is A1 plus A2, A minimum will be A1 minus A2. This is about the amplitude. But the question is, intensities are given, I1 and I2, and we have to find out final intensities. So what is the relation between intensity and amplitude? Remember one thing, that when there is a superposition, the intensities are not added directly. What is added directly mathematically is amplitudes. Intensity are calculated based on amplitude. Like if A1 is the amplitude, then intensity of the first wave is A1 square. Intensity of the second wave is A2 square. Then what is the maximum intensity? The intensity when there is a constructive superposition. So intensity at constructive superposition, that is maximum, that will be equal to A1 plus A2, A1 plus A2 whole square. Now this A1 is equal to, here A1 is equal to, if we convert it into equal, then it is proportionate to root I1. A2 is proportionate to or equal to root I2. We are deleting the constant. So A1 root I1, A2 root I2. and this I can write here root I1 plus root I2 and whole square. Then what will be the A minimum? That is A1 minus A2 whole square, and this is equal to root I1 minus root I2 and this is whole square. Okay, now A maximum and this is minimum. What they are asking, sum of maximum and minimum intensity. So we make this sum of I1 plus I2 square. How much this will be? Let's open it. So this will be square of the first term I1 plus square of the second term I2 plus 2 into root I1 root I2, and this one will be again sum of the two. This is I1 square, so this is I1 plus root I2 square is I2, and this will be minus 2 root I1 root I2. Now we have to take sum of these two. So this is the sum of these two, and this comes to here. These two are cancelled out. So when these two are cancelled out, what do we get here is 2 I1 plus I2, and keep your watch on the answers. Here we have 2 I1 plus I2. So option C is the correct option for this. So remember what we should not miss here, the relation between intensity and amplitude. Number 1, this relation. Number 2, when we want to add, it will not be I1 plus I2, it will always be A1 plus A2. Amplitudes are added up, not the intensity directly. So for intensity, we have to get it A1 plus A2 whole square. So there will be a third term which is coming here. Okay, so this is how it is done. Thank you. A boy is trying to start a fire by focusing sunlight on a piece of paper using equiconvex lens of focal length so much. Diameter of the sun is given so many meter and its mean distance from the earth is so many meter. What is diameter of the sun's image on the paper? So here we will see the sun is making image on the paper. Object is sun, image on the paper. So here we have a lens. Let us say here is the lens. Okay, here is sun and here is the image of the sun on the paper. Okay, what we are supposed to find out, what is the diameter of the sun's image? We have to find out this size, this diameter. Okay, what are the data given to us? Focal length f for lens is given as 10 centimeter. So that is 10 to the power minus 1 meter. Okay. The diameter of the sun is 1.39. This is given to us. 1.39 into 10 to the power 9 meter. Okay. Then the distance from the earth. This whole system is on the earth, so this distance is also given. This is 1.5 into 10 to the power 11 meter. Okay, now this is the object, here is the image, and what we are supposed to find out, this distance. Let this should be diameter, let's call it D. D of the image. Now we have to find this size. With the lens, we can make a very simple relation. that from the rays going from center are not deviated. So if this is the size of the sun, from this end it goes like this, and from this end it goes like this, and here we get this distance. This is the sign of the image. Now how much should be this? We have learned that the ratio of these two is equal to ratio of these two. Very simple. So if this is u, distance of the object, this is v, distance of the image, and let's call it I, and let's call it O. Then we know that I upon O, image size divided by object size, is equal to V upon U. This we have already done, and this is what our geometry says. Now I we have to find out. O, size of object, that is known to us. V, this distance is not known to us, and U, this distance, this is known to us. So if this is known to us, this is known to us, this we have to find out, then we must know V. What should be the V? Now sun, if this is U, this is V, the focal length is given to us. We know that practically this V is equal to focal length. Now to make this thing sure that V is equal to focal length, I give you a very small relation, that 1 upon V minus 1 upon U is equal to 1 upon F, or 1 upon V is equal to 1 upon F minus 1 upon U. And if we put the values here, 1 upon F, F is 10 to the power minus 1 meter, and this is minus, and this U, it has become plus here, but when we place the sign, U is negative. And how much is this? 10 to the power 11. 1.5 into 10 to the power 11. Now this is 1 upon V. So now when you try to find out this value, 10 to the power minus 1, it will go here, that is 10 minus something. And this will go here, 10 to the power minus 11 upon 1.5. See, this quantity is very, very small. This quantity is so small that it is approaching 0 in this question, and this can be very well neglected because of minus 11. So what we get? We get here 1 upon V, that is equal to, yes, 1 upon V is equal to 10. So V is equal to 1 upon 10 meter. That is 1 upon 10 meter is again equal to 10 centimeter. But what is 10 centimeter? 10 centimeter is the focal length. That means in case of sun, this factor is so small that image is formed at the focal length itself, and that can be taken as a very good approximation. So we will take V equal to F. So V is equal to F. Now here we replace it, F upon U. Now I is equal to size of image is equal to size of object multiplied by focal length upon U, and all these three data are given to us. Size of object, that is size of the sun. Size of the sun is given here, diameter 1.39 into 10 to the power 9, 10 to the power 9 multiplied by focal length. Focal length is 10 centimeter, or we can say 1 upon 10 meter, because everything we are taken into meter. So this is 10 to the power minus 1 multiplied by, no, divided by. This is to be divided by U, and U is given to us distance from the earth, 1.5 into 10 to the power 11. Yes, 10 to the power 11. Now let us simplify this thing, and when we do the cancellations, it will come to 0. This 1.39 upon 1.5 is 0.92. And here you see this will become minus 11, minus 12 and 9. So this will be 10 to the power minus 3. Okay, so again we correct it, check the answers. Here is the matching answer 9.2. We also convert it into unitary. So this is 9.2, and because we are taking it here, this has to be 10 to the power minus 4. So this is converted to this because this is the format in meter. Every calculation has been done in SI system, that is in the meter. So 9.2 into 10 to the power minus 4, that is D, is our correct option. Now we go to the next question. A ray of light traveling in a transparent medium of refractive index mu falls on a surface separating the medium of air at an angle of incidence of 45 degree. In a transparent medium, refractors, for which of the following value of mu the ray can undergo total internal reflection? Total internal reflection means it is going from denser to rarer medium. This is the interface between the two mediums, and this is normal. So if this is denser, this is rarer, we say this is the ray going, and this angle is given to us as 45, and then it become parallel to the surface. American total internal reflection. For 45, it goes like this. Okay. It should go like this. Now, if it is more than 45, it will come here. If this is 45, then what should be the refractive index of this? We know that 1 upon sine C is equal to mu. Here, C is given to us as 45. So this is 1 upon sine 45, that is 1 upon root 2 is equal to mu. Therefore, mu is equal to root 2. That is equal to 1 point, root 2 value you know, 1.44. This is the mu required to make it here at 45 degree. Now what they are asking, there is no 1.44 here. What they are asking, what should be the value of mu the ray can undergo total internal reflection? 1.50, that mu is larger than this. If mu is larger, then it is capable of bending it inside. If mu is 1.25, if mu is less than this, then it will not be able to bend it this way. Then it will go something like this. 1.33 is less than 1.44, not able to bend it. 1.10, not able to bend it. So, which refractive index will be able to bend it in total internal reflection? Answer the one which is more than 1.44, and there is only one which is more than 1.44. So only this material has capability to bend it, because we know the minimum required is 1.44. So here we have to understand what they are trying to ask us, that if this 45 is there and it is going here, to bring it inside, what should be the mu? Should it be more than this or less than this? So remember, more is the bending power. What is mu? Refractive index. It is the power of bending. So if mu is more, it will bend it this way. But if it is less than this, it will not be able to bend it even up to this one. It will go either here or here or here. So remember it, mu should be this mu what we get with this case, critical case, that is the minimum value of mu. Minimum. So if this is minimum value required, there is only one answer which is more than this. So our option is Option A. This is how we get it. And now we go for the next question. Okay. The next question says a lens having focal length f and aperture of diameter d form an image of intensity I. Aperture of diameter d by 2 in central region of lens is covered by a black paper. Here is a lens. It has a diameter d. This is center. Okay. Aperture of diameter d by 2 in central region is covered by a black paper. This d by 2. D by 2, and this is all covered by a black paper. Okay, that means light cannot pass through it. The focal length of lens and intensity of image now means after the change. So this is before and this is black and this is after. The light is passing through this, the light is passing through this. In both the cases, what is the difference of focal length and what is the difference of intensity? The two. Focal length, these options, intensity, these options. Okay. Now, look from the side. This is the lens. If half of it is blackened, like from this to this gets black. If this gets black, is there any difference in the focal length? Answer is, the focal length is formed by the prismatic action of these two surfaces. It bends it this way and this bends it this way. And we get the focal length here. It has got a certain particular curvature, and because of that curvature we have that formula 1 upon f is equal to mu minus 1, 1 upon radius 1, 1 upon radius 2, lens maker's formula. But when we make it black, are we changing this radius of curvature of this part? Answer is no. What is happening with this? What happens with this is the amount of light which is passing through this portion is cut off. So the quantity of light reduces. But the curvature is not changing. No change in curvature. Therefore, there is no change in focal length. No change in curvature. No change in focal length. So, focal length remain f as it is. Now, what about intensity? Very well. The intensity is simply the energy passing through the lens. Energy passing through the lens. If energy is passing through this lens and passing through this lens, what is the change in quantity? Answer, whatever is the change in area, that is the change in quantity. Now, what is the change in area here? The area for this, I will write it, intensity after divided by intensity before is equal to area after divided by area before. So, area after is pi d by 2 square. Area before is pi d square. Intensity. So intensity afterward is equal to original intensity I, this we transfer here, multiplied by pi is cancelled, d square is cancelled, and what we get is 1 upon 2 square, that is 4. So 1 upon 4. So this is I upon 4. This is intensity after it is blackened out. So I upon 4. Focal length was f. Intensity is I upon 4. Where is this combination? F and I upon 4. So this is our answer, that is option C. So this way we have done 10 questions on optics, that is ray optics. In the next class we will do wave optics. Thank you.